Morning. As you know, since now we have a broadcasting of this lesson, so it will be possible to be available on the website. So I will, for this reason, I will repeat the first one. Sorry for who had the opportunity to listen to it. And I will give the second lesson immediately later on. I hope that it is not too much for you, but anyway, statistics is statistics. I will start again with the same slide that I like very much. This is just a sentence that is perfect. A statistician can have the head on the oven and the feet into the eyes, feeling on average good. This is the danger and the good of the statistics. So you can draw conclusions that not necessarily are perfect because, of course, you can feel good, but you have two extremities that are not the best, like this, a oven and the eyes. Another sentence that is, again, very important to define statistics is this one. The statistics is the only science allowing different experts using the same data to achieve different conclusions. It is another danger of the statistics. However, we cannot do anything because medicine is now quantitative and evidence-based. So we need the numbers and we need to understand the meaning of these numbers. The first thing that we need to know about statistics is that this is useful to present our data. This is called descriptive statistics. So we are taking the data of a research and you must put in such a way that can be understood by others and you describe your data. Later on you try to deduct a general principle from with a logic method from your data that are limited. You are not using all the data of the world. And this is inferential statistics, the statistics that helps you to draw conclusions. The statistics deals with the variability. Variability can be due to biology because the subjects are different, because of genetics, physiology, metabolism, and so on. And because of data collection, because it depends on the operator, on the instrumentation, on the specific moment when the data is recorded, and so on. And this is the reason why all this, the data we extract are called variables, because they can vary from time to time. First of all, we need to be familiar, to become familiar with some of the new terminology that is included in the concept of statistics. The first one is the concept of independent or dependent variables. For instance, this is very easy. The example gives you exactly the meaning of this definition. If you study the factors which can influence the death of a group of patients, these factors that are the age, gender, and so on are the independent variables. And the death is the dependent variable. So you are studying something, and around this fact you have different variables that can vary. Another concept that is very important is the concept of confounding variable. It's a variable that can lead to erroneous conclusion about the relationship between the independent and the dependent variables. For example, and this is a very good example, you want to investigate if mitral valve repair gives long-term results better than mitral valve replacement in patients with the mitral regurgitation. For this purpose, you choose two different populations. However, this population include other variables which can confound the outcome of the dependent variable. On the dependent variable, it is the outcome, whereas the independent variable is the surgery you are doing to the patient, repair or replacement. These confounding variables can be the age, ejection fraction, the dilatation of the cavities, reversibility or not of the pulmonary hypertension. The etiology of the MR can be primary, secondary, ischemic, rheumatic due to the prolapse, chordal rupture, and so on. It can be acute or chronic. So there are a lot of variables that can have an influence on the result of your study. How can we deal with the confounding variables? That is mostly what we are doing every day when you are doing a research. You control them by matching, by randomizing, or by statistical control. So you need to know how to deal with that. But one thing you must be very careful about, because one of the most important confounding variables is the possible bias of the researcher. finding a statistically significant result is almost always more interesting than not finding a difference. And this means that we are part of the variable. So because sometimes you are not including a case, you are including another case, and so you can, the bias, your bias can be the most important confounding variables. Just a global definition of the variables is the following. We can define them continuous, when the observation can be expressed as a continuous quantitative value, age, blood pressure, and so on, or categorical. These are variables that are non-representing quantitative values, and the subject can be included only in one category. They are nominal or ordinal. Nominal is very easy, gender, dead or alive. There is no other possibility. You can be either dead or you can be alive. Or ordinal, when the categories can be ordered. Typical is the NIA class, 1, 2, 3, 4, MR grade, and so on, TR grade, anything that can be ordered. In general, a variable with only two values is a categorical nominal variable. There is no way. In general, is defined by a word, like dead, alive, black or white or anything you want. A variable with 6 or more variables should be treated as a continuous variable. A variable in the middle, 3, 4, or 5 values, in general, is to be treated as a categorical ordinal variable. This is important because in your statistical program, ask you which is a categorical variable and which is a continuous variable. So if you need to put the right definition to your variable. The categorical variables is the first part of our talk. So you imagine you have a table. You need to put to express your categorical variable. This means that you must express them as a counts and a percentage. Don't put only the numbers, but you must put also the percentage, because if you are comparing two groups that are different, it's difficult to understand which is the weight of the variable in the comparison of both groups. The percentage is called prevalence. Means, for instance, the prevalence of diabetic patients in our coronary population is 38%. 220 out of 577. We have the trend to say incidence. Incidence really is not correct. The correct term is prevalence, because you need only one observation. Incidence, you need more than one observation, but this is another story. The ordinal variables, when you have to report the NIA class, for instance, of your patient, or the mitral regurgitation, anything you want, should be reported as counts and percentage, not as mean. Sometimes in the past, we were accustomed to say NIA class was a mean 2.3 plus minus something. This is not correct. Now they don't allow anymore you to write like this. For instance, the MR grade that you can see here is ordered between 0 and 4. You have 5 classes, and you must say the counts. You must report the counts of each classes and the percentage of each classes. Let us say the prevalence or the grade of mitral regurgitation. You cannot say 1.4 plus minus 0.9, like in this case. Now let's go to the continuous variables, because we need to understand how we have to write our continuous variables. When you describe a data set, you have to provide every time a central tendency and a measure of dispersion. The central tendency is the mean or the median, and the dispersion includes the standard deviation or the interquartile range. Here there is an example. You have the age of this patient. You have the mean, that is the sum of the data divided by the number of observations. In this case, it's 35.3. And you have the median. The median is a different concept. Is the value below which 50% of the observations falls. You see that the median here is 33.5. So you have the possibility to use both one of the two methods. The median, however, is a measure of location. This means tell us where the data are. We do not need to know all the data to calculate the median. If we change the smallest values in the smaller values and the highest values in even higher, the median doesn't change. I want just to show this example. You have here 7 numbers. 1, 2, 3, 7, 8, 9, 9. The mean is 5.6 and the median is 7. Now let us change the first three. 1, 2, 3 becomes 1, 1, 1. And let us change the last three. 8, 9, 9 becomes 29, 56, 78. You see that the mean changes dramatically from 5.6 to 24.7. But the median remains exactly the same. So there is something wrong in this concept. Because the median does not work with the value of the variable, but with their position in a list. So it works with the rank of each variable. As the median does not use all the information we have, it is less efficient than the mean, which anyway does use all values of the data. As the choice between the mean and the median depends on the distribution of the variable, the next step is to understand which is the distribution of the variable, because, and this is an important concept that you must have. The variable can be distributed normally or not normally, or non-normally. This is not something we have to do, but we have to use the computer that tells us what happens. Here you have an example. You have 160 person, and you are just evaluating the end diastolic dimension before a surgery. You have here the arithmetic mean is 49.4, the median is 50, more or less are the same. And here is the test that tells us that everything is okay, because when it's normally distributed, the mean and the median correspond. And here you see the Gauss curve and all the values that more or less are going close to the Gauss curve itself. How can we report the centrality and the dispersion of this normally distributed variable? The centrality is indicated by the arithmetic mean. The dispersion by the standard deviation. That I think all of you know. The standard deviation shows the percentage of values included in a certain range. The properties of the standard deviation are very interesting. Let us assume that the mean age of a population is 36 years plus minus 4. This means that from the statistical point of view that we are evaluating a normally distributed variable, and between -1 and +1 standard deviation, you have 68% of the population. So they are concentrated there. So between 32 and 40 years, 95% of the patient or the population will be included between 2 standard deviation, in this case 28 and 44, and close to 100%, a little bit less, will be included between 3 standard deviation, that will be 24 and 48. So with the mean and the standard deviation, you know a lot of information of our population, taking into account the standard deviation. When you have a continuous variable, unfortunately, sometimes it is non-normally distributed. It's not unfortunately, but you see that when a variable is not normally distributed, things becomes a little bit more complicated. In general, this happens when mean and median do not correspond. Here you have ICU stay of 115 patients. You see that the mean is 5.9 days, but the median is 3 days. And this test tells us that there is a non-normal distribution. When you are going to see the Gauss curve, you see how big is this one, and there is nothing here. Evidently, is non-normally distributed. You need to report again the centrality and the dispersion of this variable. Centrality is indicated by the median, as we know, and the dispersion is indicated by the interquartile range, something that has to do with the ranking of this patient. For instance, sometimes you read in a paper, Euroscore 2, median 8, with interquartile range 5.4, 11.9. What means? First of all, I want to remember, when we have a mean and standard deviation, the mean is exactly in the middle. Standard deviation is symmetric. Here is totally asymmetric. What means this? It means that you divide all your population in 4 parts. 8 is the median. So 50% are here and 50% are here. 5.4 is the first quartile, means 25% are here and the remaining are up. And 11.9 is the third quartile, and it means that 25% have a value that is higher than the 11.9, and the remaining is lower. At the same time, you know that 25% of the patient is in between 5.4 and 8, and another 25 is between 8 and 11.9. So you have a lot of information, but not necessary. Here you can have the maximum can be 20, can be 50. Doesn't matter from to evaluate the median. Calculating the median and the quartile range, honestly, is very easy. But, of course, I want just to tell you one thing. Remember that a long time ago, all this calculation has to be done by hand, with just with using your brain and doing a multiplication, a division, and so on. Things changed when the computer arrived, because all the things I am telling you, you just push a button and have all the answers. You don't need to calculate anything. But when I started the first statistical steps of my life, I just calculated the chi-square manually. So it means, imagine now what it means to calculate a complicated test. You take 1 day only to understand one test. But here, just I want to show you the concept. I told you that the median deals with the rank, with the position. You have here 25 values, and these are the rank of the values, starting from the first till the number 25. You have 25 ranks. You add 1 and divide by 4, and you have the result is 6.5. So you identify 3 ranks. The first one is the number 6.5 here, between 6 and 7. So this is the value 9 to 13. One is 9, one is 13. So the mean is 11. And this is 25th percentile. The second rank is 13. This is the median. And this corresponds to 23. And this is 23. The third is 19.5. Again, between 19 and 20. Here is 47 and 55. The mean is 51. So basically the median is 23. This is the middle rank. 11 is the 25th percentile that you take from the 6.5 rank, and 51. So this is the system. The concept is that you don't need to know the numbers, but only the position. Of course, here you have a 56, 190. You can have 2000. It's always the same. It doesn't change anything. So this is the concept that allows you to understand that anytime you read the median, you have a position, but not the values which you are looking for. As we said, this is what I said before, that it does not take into account of the specific measure, but only a measure higher or smaller of the central value. Many of the most statistical tests, as the t-test or the ANOVA, assume that the data we are analyzing are normally distributed. They are preferred as they analyze the real measure, not only the position they have. So let us say that the statistical strength of a test that is using the data is by far better than the strength of a test that is not using the data, but only the position. These tests are called parametric tests. So these are the most important tests we have, like the chi-square is a parametric test, the t-test, T of student t-test is a parametric test. Many variables, unfortunately, do not meet the assumption of parametric statistical test, because most of them are non-normally distributed. In cardiac surgery, for instance, there is no way that the ICU stay is non-normally distributed. You cannot do a mean of the ICU stay because you have nothing. In the curve of Gauss, there is the left side, there is nothing, because you cannot have -2, -3, -4. So these are not distributed, normally distributed. Using a parameter statistical test can give misleading results. However, we don't know exactly how much non-normality has to be to have a wrong result using a parametric test. Why? Because most of the parametric tests are allowing some can be used even for non-normally distributed, because they are not very sensitive to some deviation from normality. So sometimes you can use some statistical trick, let us say. Sometimes a variable is not normally distributed. You do a transformation of the data. In general, it's the logarithmic transformation, and the data become normally distributed. You use a parametric test. Unfortunately, if both groups you are dealing with, after transformation, one of them is still non-normally distributed, you have to use another test. You cannot use a parametric test, and you must use the test that is called non-parametric. So this is the lesson, the first lesson I gave you last time. I think that at least for whom was here is just a reminder of what happened. And if you want, I can keep going. And you want to have some rest, 5 minutes, or you want to keep going now?